So I'm going to be talking about, so yesterday I talked a little bit about sources of continuous gravitational waves. So these are gravitational waves that, unlike the ones that have already been detected, these are ones that are persistent. These are ones that are lasting essentially forever. Yeah, as basically, practically speaking, they last forever. They don't really change that much, and they're sources that are that are always there. So today's talk is going to be mostly sort of a data analysis talk. Searches for continuous gravitational waves, in some ways they're similar to searches for these binary mergers, these compact binary coalescences. In other ways, it's a very different problem. So there are a lot of different methods to search for these CW signals. I'm going to talk about, mostly I'm going to focus on the one I use. It's again a match filtering method. The difference is we end up having things like 10 to the 17 results. So we have enormous data sets. And so when you're doing searches for CWs, a lot of times actually running the match filtering algorithm, actually doing the calculations and calculating the significances, that's sort of, I don't want to say the easy part, but that's sort of the part that's kind of straightforward. And the hard part is figuring out what to do with the 10 to the 17 results when your detector is also real, your signal is weak, your detector is very disturbed, or at least your detector has a lot of things that are not quite characterized very properly yet. And yeah, so let's see. So what I'm showing here is a screensaver from Einstein at Home. And this is sort of a little plug. So Einstein at Home, I don't know if you all have heard of, let's say, SETI at Home, where you can, use when you're not using it, you can donate your computer's processing power to search for, I don't know, signs of aliens from outer space. Well, you can also do that for actual, gravitational wave signals, as well as for searches for gamma ray pulsars. So if you're interested in, you have your computer lying around, it's not doing anything. If you're interested, you can sign up for this. I think you can also join teams and things like that, and it's all fake internet points, but I think you get a free screensaver at the end of it. So this is sort of a plug, not a very good plug for Einstein at Home. But yeah, I should say that the people who, there have been actually a bunch of gamma ray pulsars that have been detected using Einstein at Home. And so if your computer is the one that ran the sort of the computing job that actually detected the pulsar or the continuous gravitational wave, I think what ends up happening is the director, he digs up, because I think everyone's supposed to be more or less kind of anonymous. Anyway, somehow they figure out your contact information and then they email you and say congratulations, and you get a certificate and everything like that. So that's also fun. So just a reminder, for the standard continuous gravitational wave searches, the sources, which are neutron stars with asymmetries, the sort of general paradigm is that you have, right, a neutron star is born, you have a star going supernova, and when it's first born, it could have these asymmetries, or it's more likely to have these asymmetries from this violent explosion, and then as time goes on, it smooths out. This is a very simplistic picture of what's going on, because young neutron stars can also undergo glitches. They can undergo sort of these star quakes and these structure reformations or sort of magnetic field rearrangements and things like that. And all of these, or they could accrete matter. They accrete material. They might be in a binary. And all of these are different ways to get sources that might emit continuous gravitational waves, or that should emit continuous gravitational waves. Yeah, so the issue is not necessarily whether or not they emit these continuous gravitational waves. The issue is whether we can detect them, if we're sensitive enough to detect them. And just a reminder, in order to get gravitational waves, you just need some kind of mass asymmetry, and so therefore a time-varying mass quadrupole. And here we have, so the scenario I'm going to be talking about, or the mechanism I'm talking about, is essentially just a mountain on a neutron star. There are other mechanisms, like you could have basically mass currents, so the equivalent of charge currents, let's say. You could have mass currents that are going rotating in the interior of the neutron star, and that can also give you gravitational wave emission, or that should also give you gravitational wave emission. I'm going to be focusing on the mechanism just because we think this is the one that's most likely to give us a detection. So the physical waveform at the source is pretty straightforward. It is sinusoidal, and it can simply be defined by its the frequency, so how fast it's spinning, and the frequency derivative, so how much it's slowing down, right? Because all these things are slowing down over time. So the let's see. Yep, the waveform at the source is relatively straightforward. In this What I'm showing up here are the formulations for the cross and plus polarizations. And so they're both just sinusoidal functions of this phase 5t, and then iota is just the inclination angle. So what angle, so if it's spinning like this, how are we viewing it? Are we viewing it on, right on we're looking at the spin axis, or are we looking at 90 degrees, that sort of thing? The problem is everything is moving. The Earth is moving, the Earth is rotating once a day, and the Earth is also revolving around the sun. So this means that at every point in time, the signal that we're receiving is actually being Doppler shifted, right? Especially if you go around the sun. So there's a daily Doppler modulation as the Earth rotates. There's a yearly Doppler modulation as the Earth orbits around the sun. And the tricky thing is that this Doppler modulation is different for every single position on the sky, right? Something over there is going to have a different Doppler modulation, a yearly modulation in particular, or that's the strong one, a yearly modulation in particular than something on this part of the sky. And so you can see that this quickly becomes really expensive because you have to search a slightly different waveform. You have to take into account a slightly different kind of Doppler modulation for every single part in the sky. But if you do have, you know exactly how the Doppler modulation is going to look like, you can then work backwards and retrieve the original signal, and then in the in the frequency domain, it should be something pretty spiky, let's say. A frequency, well-defined frequency, maybe a frequency derivative. Maybe it's spinning down over time. So this is just a couple of numbers to say what kind of things are we talking about when we say CW signals are expected to be weak. So naively, let's look at the very top. This is the strain you might expect. So order of magnitude 10 to the negative 24. This is for something with a sort of standard moment of inertia, so standard neutron star mass and also the radius. This is saying, let's say it's emitting gravitational waves at 1,000 hertz. This means it's spinning 500 hertz, 500 seconds, so millisecond neutron star basically. This is saying it's 1 kiloparsec away. The galaxy is roughly tens of kiloparsecs wide, let's say, in the stellar materia at least. It's around, I think, 15, 20 kiloparsecs radius. We're about 8 kiloparsecs away from the galaxy. So we're looking for things that are within the galaxy. So this quickly becomes too weak when things are outside the galaxy. And then the ellipticity, right? We already talked about the ellipticity, how bumpy the neutron star is. So let's see. If we search over a time, let's say t-coherent. So I'm saying t-coherent, t-co, because that's the coherent time over which we're searching, right? So we have this stretch of data, and we're going to search the entire stretch of data for a coherent signal. There are different ways you could do this, but let's say we're doing the entire stretch of data for a coherent signal. So trivially, the number of cycles, so the number of oscillations is proportional to t-co, right? The longer you have t-co, the more cycles you're going to get in there. The SNR squared is also proportional to the number of cycles. This is slightly less trivial, but basically for any kind of match filtering process, what falls out is that, what's your SNR? Your SNR squared is going to be, you calculate it by taking the inner product. If you have a signal, then it's taking the inner product of the signal with the waveform, right? And so if that's just the inner product, so that's just an integral. That's an integral over time, right? And so especially for a continuous wave signal where everything is just oscillating back and forth, then if it's just an integral over time, then that number of cycles is just going to increase linearly the longer your t-co is. And so all of this means that your signal to noise ratio, your sensitivity to signals, goes as the square root of time. So the longer you search, the more your SNR increases, but it increases slower than linearly, right? It increases like the square root of time. So if we can compare, just do some rough back of the envelope calculations. For binary events, the typical strain is around 10 to the negative 21, 10 to the negative 22. So these are for the loudest LIGO-Virgo detected binary black holes is around 10 to the negative 21. For the quieter ones, it goes down to 10 to the negative 22. All these events, let's say the coherent time is around 1 second. Many of them are less, but order of magnitude 1 second. So for a CW search, let's say we do a CW search and we search for 3 months and we get around 10 to the 6 seconds. So the SNR increases then if we compare from 1 second to the 10 to the 6 seconds, it increases by the square root of 10 to the 6, which is 10 to the 3. Theoretically, being equal, the SNR increases by 1,000 when we go from 1 second to 10 to the 10 to the 6 seconds to 3 months. And so then that kind of compares, right? So then if we can detect binary signals of 1 second with a strain of 10 to negative 21, we should be able to detect CW signals with a strain of 10 to negative 24 if we're searching over 3 months, let's say. This is very hand-wavy order of magnitude. What do we mean, though, by, so what do we mean by things like SNR and, strain sensitivity, things like that? The way I like to think about it is, so what you're seeing here is a figure of the strain noise, or what's sometimes called the amplitude spectral density, and versus frequency for the three of the currently operating gravitational wave detectors. You can think of this, so the way someone has described to me once is the amplitude spectral density is kind of like the standard deviation, right? Or the uncertainty. So your detector is always going to be moving a little bit. It's always going to be wiggling. It's not perfectly still because there's lots of other sources of noise in there that you can't get rid of. Things like thermal noise, right? Because things are not at 0 Kelvin. So there's always going to be some Brownian motion in there that's going to be pinging your mirrors and is going to be moving them slightly. Or things like seismic noise, because we're on the Earth. Seismic noise, and you could try to get rid of it by subtracting it out, but there's a lot of sort of low-level seismic noise that's really hard to get rid of. There's also the quantum noise of the laser, right? The laser itself is, it's powerful, and then that's also going to affect the movement of the mirror and things like that. There's also other unforeseen sources of noise, like I talked about the ravens briefly. Like ravens pecking on your detector are going to cause sort of little bits of transient noise. Other things, sparks. So if your air is really dry, right? If your air is really dry and the air is really dry around one of the detectors, Hannover is in a desert. If the air is really dry, you could just have static shock, just sort of hearing. When it gets a chance, and that could actually cause little blip glitches. There are little glitches in your detector. Other things, there was one, right, so these are the things I was talking about, the little sparks in the air as well as the ravens pecking, that's sort of transient, right? Those are short-term disturbances. You can also have long-term disturbances that basically look like continuous waves. They're only at one frequency. And I think a fun example of that is blinking LEDs. Blinking lights, that is actually enough to cause a visible disturbance in the detector. And that was a problem, I don't remember how many years ago, but a previous run, they realized that there was, so there's a whole team that at the detectors and working off-site that are trying to characterize and get rid of as many of these disturbances as possible. And so there was this one that they were really trying to dig into. They traced it back, right? They plugged in sets of different combinations of the electronics, and they traced it back to a blinking LED. That's all it took. And so it's things like that, things that you normally wouldn't think about, that actually cause a lot of problems for searches for continuous gravitational waves because they're very weak and because CWs are defined by a single frequency. Blinking LEDs are also defined by a single frequency. Another problem we would get are the frequency, so the power lines, right? 60 hertz power lines. Big issues in a lot of countries. 50 hertz power lines, big issues for Virgo in Italy, right? 60 hertz is the problem for LIGO, the two LIGO detectors. And so if you have something at around 60 hertz, that's kind of tricky. That's kind of difficult to really search for. At the very least, your sensitivity really decreases because are you sure what you're seeing is a pulsar or are you just detecting the power lines? Another thing, the violin modes. So all of these mirrors are suspended, right? Mirrors are suspended in very complicated pendulums, just so they could, just so you can basically reduce the movement of the mirror as much as possible. So they're suspended in very complicated pendulum sort of, just in systems. But the suspensions, right? The suspensions have some kind of resonant frequency. And you could actually excite that resonant frequency, right? And so if that happens, these are called the violin modes. So there's a couple of frequencies in the detectors where it's a wide frequency where you really have to be careful exactly what you're claiming in that area or when you're searching in that area, because are you actually detecting a pulsar or a CW signal? Or are you just detecting the vibrations of the suspensions? Yeah, so with all of this said, right, lots of sources of noise in the LIGO detectors and in the gravitational wave detectors, and there are a lot of people working really hard on trying to decrease the noise sources. But at the end, that's what we have. We have this noise, we have the sensitivity curve. So the sensitivity, you can think of it sort of as like the your uncertainty on your measurement. So your uncertainty on your measurement, if you have a really loud signal, like a compact binary coalescence, and you're uncertain, if you have a really loud signal, that's 10 to the negative 21, and if your uncertainty is 10 to the negative 23, you can still be pretty sure that you've got something below zero, or sorry, above zero. You've got something significant. If your signal is actually, the strength is actually 10 to the negative 24, and your uncertainty is 10 to the negative 23, but your signal is always there, is always persisting, then you're going to have to search over a much longer period of time to build up the SNR. So you have to build up the SNR until it gets above your uncertainty enough so that you can say, oh yeah, we've definitely detected something at 5 sigma or greater, that sort of thing. But realistically, right, so I was starting to talk a little bit about the issues when you're actually searching for CWs. And realistically, there are a lot of, so those are the detector issues. There are also fundamental issues with the search. And the issues are basically your computational cost and your trials factor. So with the computational cost, so the first line here is a Taylor expansion of the CW of the signal, a phase of the signal, so how it's rotating around in the source frame. And that is just basically, so just a Taylor expansion, where here t is the time and t0 is the time at which you started searching. So t minus t0 is the entire time that you care about. And if you convert into the detector frame, then you need to do all of these conversions, right? Because, like I said, the signal at the source, relatively straightforward, sinusoidal. Signal at the detector changes as it's rotating and orbiting. And not only that, you have to do all these corrections, these relativistic corrections, like we talked about the Shapiro delay, right? And gravitational redshift and time dilation. So you have to take into account all of these when you're doing your search for approximately every moment in time, or every moment in time that's sort of relevant, basically. So you have to do all of this. And then you want to avoid losing signal coherence, right? So if your signal looks like this, and then your waveform that you're searching over is slightly off, but you're searching over a short period of time, you're still going to match it pretty well. But if your signal looks like this, and your waveform looks really different, then as time goes on, you're going to get farther and farther away from the true signal, right? And you want to avoid that. So you want to make sure that your signal maintains coherence. What does that mean? That means we look at the very top with the signal phase just the source frame. Let's look at the source frame. We want to keep the thing on the left, let's say, constant, or let's say we want to keep the delta phi. We want to keep it within, let's say, 1, or we want to keep it constant. That's it. That just means, what does that mean? That means if we look at the first term, or the first term in the brackets, the frequency times t minus t0, well, that's just how long, t minus t0 is just how long we've searched for, so that's just t co. So that means if we want to keep this sort of relatively small, that we have, or constant, that we have to have the steps in frequency to be approximately, or to go as 1 over t co, right? We want, this is f times t co, so we want delta f to be approximately 1 over t co. And similarly, we want delta f dot to scale as t squared, or sorry, 1 over t co squared, delta f double dot to scale as 1 over t co cubed. Things like f and dot f and double dot f, I realized I was saying. So f is just the frequency, f dot is just the spin down, or the first time derivative, f double dot is the second time derivative. Sometimes these matter if you're looking for signals that are changing really rapidly, so maybe really young neutron stars that are still evolving relatively quickly. So when you do all of this, so let's say you're doing a search for one sky position, and you're looking at a young neutron star, so you have to go to f double dot, or the second time derivative. That means you're looking at the number of trials being related to t co to the 6. And I'm saying 6-ish because there is also a little bit more dependence on some other things and how you develop or how you set up your code. And similarly for an all sky search, right? Because for an all sky search, you have to search over the entire sky, so you have a lot more, so you have to deal with that. But you also maybe, because you're searching over the entire sky, maybe you only go down to the first spin down. Why am I having so much trouble with this today? All right. So basically, what we're looking at is the number of trials increasing with a really high power with your coherence time. And this is tricky, right? You want a longer coherence time so you can increase your SNR, but SNR only goes as the square root of the time, whereas the number of trials, and therefore your computational cost, goes as the 6th power of the time, right? So it's getting more expensive a lot quicker than it's getting more sensitive. And the other problem with the number of trials is, let's say you have a really weak signal, And it's hard to know exactly it's hard to know if the signal is actually there in the data if you can actually find it. But if you have 10 to the 17 search results, at some point your fluctuations, just plain fluctuations in the noise or Gaussian fluctuations could cause a spurious candidate to just randomly pop up above your significance, right? And so when you do all of that, when you do all these searches, you have to take into account the fact that, we could search over more templates, and more templates, more types of signals. We could do all these things, different kinds of signals, but the more signals we search, the more trials we increase, the more we kill our significance or potential significance, right? If you play the lottery 10 to the 17 times, you're likely going to get something. You play it once, you're not going to get anything, right? So that's the difference. That's the difficulty with the number of trials here in this scenario. So with this whole issue of the computational cost scaling, like the number, like your time, there's a couple of different strategies, and the one I want to focus on is what we call a semi-coherent search, right? So first I said you could have 3 months and you could search it coherently, and that's going to give you a really sensitive search, but that's also going to be pretty expensive. What you could do instead is say, I'm going to divide it into a certain number of segments. I'm going to divide my search by 3 months into weeks at a time, and I'm going to search each week for the signal separately. And I'm not going to require that the signal that I find be coherent between the different weeks, right? So that means, I don't want to draw. So that means you lose a little bit of because you're no longer requiring the signal to be coherent, which means that maybe you pick up some noise over here, you pick up some noise over here, maybe that noise adds up, and so you have to do things like that. So your search sensitivity is going to be a little bit different, but your cost is going to drop dramatically because the expensive part of the search is going to be searching coherently within these much shorter time segments, and then you just add things up incoherently, right? So you find the result for your first segment, and then you find it for your second segment, and et cetera, and then you just add up the results. Well, you don't have to add them up. You could also average them, or you could find other ways to sort of combine your results. But at that point, it's relatively cheap. It's, if you're just doing addition, that's really fast. And then again, your sensitivity, so you lose a little bit in sensitivity, but you drop your computational cost by a lot. And practically speaking, this is what we need to do for anything that's not a search around a known pulsar. Let's see. So what you're seeing at the bottom over here. So I talked about how you divide your data into different segments, and signal in each segment. Well, that signal is evolving in each segment, right? If the signal is slowing down, if you're searching for it over here in the first segment, you should be searching for it over here in the second segment and over here in the third segment. So this is what it's showing. This is what this figure is showing, is that in each different segment, you say, all right, I'm looking for the signal up there. And then the second one, you say, okay, if I move forward in time, I expect it to be over here. So the 2F, so 2F is sort of a standard detection statistic we have. It's the optimal match filtering statistic. And so what we do is we combine 2F, we take note of what 2F is at every single segment, we add it all up, and then we average it out. And this is the statistic we end up using. So the most straightforward scenario is when you have a known pulsar, right? We talked about this yesterday. If you have a known pulsar, you know the exact ephemeris. We talked about how some of these pulsars, the ephemeris is known so well it's known in the uncertainty is 10 to the 14, 10 to the 15, right? So you know exactly where you expect your gravitational wave signal to be if it's this type of signal. You know exactly where it's expected to be, and so all you have to do is just search one signal template. You just have to search one signal template, or you might search a couple because maybe you're not completely sure, maybe you want to try different methods and search methods and things like that. This is really straightforward. In some ways, it's nice because for a known pulsar search, you only have to search one template, and so you can get really good and really sensitive because you know exactly where you expect the signal to be. In other ways, it's bad, right? Because we talked about, how the neutron stars are spinning down and they're emitting energy. With a pulsar, if we detect pulsations, we know that it's definitely emitting a bunch of its energy and magnetic dipole radiation. So then the question becomes, if it is emitting gravitational waves, how much energy is there left over to be emitted in gravitational waves, right? So you can look at it from that standpoint. But then you say, well, with the pulsar, you might expect a larger magnetic field, and with larger magnetic fields, maybe you can get some sort of deformations in the crust. So maybe with the pulsar, you actually for detecting a CW. So this is so it's a little bit tricky, what's your best source and things like that. Next best case scenario is we have a no neutron star, like a neutron star in the middle of a supernova remnant. So what you can, the supernova remnants, some of these supernova remnants, like we talked about the crab, right? The crab nebula, crab pulsar, all these things are combined. So with the crab, it's in a supernova, it's also a pulsar. There are a lot of supernova remnants where we don't detect any pulsations from anything in the middle. And so what you do there is you can do things like, you try to look really deep. I mean, you search for pulsations, right? But what you can do to detect a neutron star is you can search for thermal emission, so maybe X-ray emission. Especially if that neutron star is young, it's still going to be pretty hot and it's still going to be emitting, let's say, thermal X-rays. So you can do things like that to search for known neutron stars and figure out where in the sky those are. And when you do that, you still have to search over frequency and spin down and maybe second order spin down, but at least you know exactly where in the sky it is. So you don't have to, for every point in the sky, have it calculate a different Doppler modulation pattern. Sort of, in some ways, the worst case scenario is that you have no idea what's going on. But, no, sorry, that's a little bit cavalier, is that you have, you want to do an all sky search. You want to do an all sky search because they're estimated to be about 10 maybe 10 to the 9 neutron stars in the galaxy. We know about 2,000, less than 3,000 of these because we've detected them mostly as pulsars or sometimes in binaries. That means there are tons of neutron stars that are still hidden from us, and that's kind of expected, right? Not every neutron star is going to be emitting, is going to be acting like a pulsar, and even if they are pulsars, they could be pointed away from us, so we're not going to detect them. So this is tricky this is computationally difficult because right now you have to search every single sky position. You still have to search all your different signal templates, your waveforms for the frequency and spin down that you care about, your range that you care about. The good news, I guess, if you think about it, is that, well, there could be, right, because neutron stars, they cool, if they're not interacting with anything, then they could just be completely invisible. If they're completely invisible, they could be right around the corner, and we might not have detected them yet. This is a good thing about all sky searches, is that we expect there to be many, but then the search itself is very complicated. And so when we run these searches, whenever we decide, well, how do we decide which pulsars to search for, which supernova remnants to search for? We always say, can we potentially detect something interesting? Could we say something interesting with this by searching this source? So what you do, right, you compare estimates, you take your estimate, you calculate, be releasing gravitational because you know exactly how much it's spinning down, so you know exactly how much kinetic energy it's losing, or because you know its age, so you can do some guesses, and I'll go over that a little bit more. And then you say, well, what's my search sensitivity? I expect the signal to be less than this amount, but I can only find signals that are, if I'm only sensitive to signals that are higher than this, then it's not worth searching the signal. It's not worth searching that particular source. And, I don't know why I did that. Anyway, yeah. Because again, we will care about the rotational energy or the loss of kinetic energy and do things like we know it's going to be, if it's a pulsar, we know it's going to be emitting magnetic dipole emission, also emitting continuous gravitational. So there are three, and this gets a little bit jargony, but there are three, rough speaking, three kind of categories of searches. So you could have your targeted searches. So what this is just a rough figure showing search sensitivity going up on the vertical, how much information you have about the source going to the right, but your computational costs increasing to the left. So you could do a targeted search where you have a source with a full ephemeris, so a known pulsar. You know exactly how it's rotating. You know exactly how that rotation is changing. You could instead do, and that's the one that's going to be the cheapest because you have the most information about it. You only have to search one or a few templates. And it's also going to be the most sensitive because you know basically exactly where to look. In the middle, you have your directed searches. Your directed searches, you have a source with a known sky position. So you know what part of the sky you're going to direct your telescope at. Let's say you're going to direct your search algorithm to. So that's a directed search where it could be a neutron star in the middle of a supernova remnant. It could also be a neutron star in an accreting binary. So you know where it is, and you also maybe know the binary parameters, but you don't detect pulsations, so you don't know exactly the frequency of the gravitational wave signal you need to search. And then you have all sky searches, pretty straightforward. You assume nothing, and this is the lowest search sensitivity, the highest computational cost, but in some ways maybe the largest gain. The other thing that all sky searches kind of have an advantage with is, let's say you run your targeted search or your directed search, and you're running a search on one individual neutron star, and you don't detect anything from that neutron star. The most you can say is that that individual neutron star does not have any mountains higher than blah. But maybe that neutron star is different. Maybe that neutron star is just older, evolved enough. Maybe that neutron star interacted with something, and so that caused the, whatever mountains to smooth out. The all-sky search, instead, you can say something about the population of neutron stars as a whole. So this question of which sources are promising. So you know how fast it's spinning down. If it's spinning down, you can calculate how much energy is being emitted, or it is being lost, I guess. How much energy could be emitted in gravitational waves. And you say, all right, so if I'm calculating the energy that's being lost due to the fact that it's spinning down, or that I can calculate based on the fact that it's spinning down, and I say that's the maximum amount of energy that's available to be emitted as gravitational waves. Right, so we said that it's losing kinetic energy, and that energy is going into let's say, the magnetic dipole radiation or anything, electromagnetic radiation here. Could also be going to CWs, continuous waves. So I'm just saying here, physically speaking, the maximum amount of energy that's being emitted, let's say it's all going into continuous gravitational waves. Can I do better than that? Can my search go deeper than that? Because then, if my search can actually go deeper than the spin down limit, then I can start to say things like less than 10% of the energy that's emitted is going into gravitational waves. Less than 20% of the energy emitted is going into gravitational waves. And so, so this is just a reminder. This is the pulsar, again, the pulsar PP dot diagram. Just a reminder that the LIGO-Virgo bands, the current generation of ground-based detectors, can search pulsars in this, or neutron stars in general, in this range over here. And so the things that are most interesting are the ones at the very top. In some ways, the things that are most interesting are the ones at the top, which are usually the younger ones. They're younger ones, and you might expect a priori to have larger signals coming from younger ones. So right now, jumping right into search results. So what we're seeing here are the first search results for a search on known pulsars, targeted search on known pulsars in advanced LIGO. There's a lot of points on here. This plot is very complicated. Let's see what we're looking at. On the vertical axis, this is a combination of different things. This is, on the one hand, the strain sensitivity. So what you're seeing, the bunch of lines, this is an estimate of how sensitive the detectors were. I think this is LIGO. Yeah, this is O1. This is LIGO only. On the horizontal axis, just the gravitational wave frequency. All of these triangles that are pointed down, these are the calculations for each pulsar. So each of these corresponds to an individual pulsar, and this is the spin down limit for that pulsar, right? So for each pulsar, we know how fast it's spinning down, we know how much energy could be emitted, we know what's the max total gravitational wave strain that could be coming from this. So each of these triangles indicates the spin down limit for that pulsar. Each of these the circles, the red circles, the little circles, these are the results from the initial detector. The blue stars are the new results. So these are the new upper limits on the strains. And the ones that are most interesting are these young pulsars over here, where you see the blue stars surrounded by an extra circle. That means that for that young pulsar, we've actually surpassed the spin down limit. And that means we've started to say interesting things. Like let's see, do I have this on here? Yeah. For Vela, for instance, the Vela pulsar, we can say things like less than 1% of the spin down energy is being emitted as gravitational waves. For the Crab pulsar, less than 0.2% of the spin down energy is being emitted in gravitational waves. So you start playing this game with these really young pulsars, and then you start to constrain how much energy is being emitted in continuous gravitational waves. I also said that the Crab pulsar is very difficult to search for. Its frequency is around like 59.5, 0.6, or its gravitational wave frequency is around there. And the mains frequency of the US is 60. So you can see that big vertical line right next to the circle with the crab. That just shows you how bad, I think, the sensitivity, how much it drops, right around 60 hertz. And I think, 1,000 hertz, I believe, the violin mode, the harmonics of the violin mode, 1,000 hertz, 500 hertz. Don't quote me on that, but I think that's where those are. Yep. Okay, so the question is why are there a lot at higher frequencies? So these are the millisecond pulsars. So yeah, and this is simply because if you look at this figure, right? So this is the LIGO Virgo band, and in this LIGO Virgo band, only the most of the pulsars are going to be in the millisecond pulsars, just because we cannot go, right? If we want to go to other ones, we'd have to go to lower frequencies, and we can't do that with this current generation. So we end up detecting, or we end up doing a lot of searches for millisecond pulsars, which is not. It's tricky to say whether or not whether this is good or bad, right? Because because the strain goes like the gravitational wave frequency, right? So if it's spinning faster, the gravitational wave frequency is faster, and then therefore the strain is going to increase. But here's the problem. Millisecond pulsars are old, right? They're really old, and they've just been recycled. They've been spun up. If they're really old, then their their ellipticity, epsilon, you're going to expect that to be smaller. So you're not necessarily, it's tricky to say whether you would actually expect these to be the best sources. And also millisecond pulsars, right? Millisecond pulsars are at the bottom of this pp dot diagram. This means they're very stable. This means they're spinning down very slowly, right? So they're rotating really fast, and that rotation isn't changing very much. If that rotation is not changing very much, you can already say if the spin down is very small, then the amount of kinetic energy it's losing is going to be very small, right? And so are we really expecting to get gravitational waves from millisecond pulsars? It's unclear. Best source would be, right? We say young pulsars, but or young neutron stars. It's not a very clear cut case. What are the best sources to be looking for? So what we do then? So I've just told you, all right. So these are the upper limits on the gravitational wave strain from these pulsars. What's interesting is working backwards and saying, based on this strain and based on the distance, how far it is, what can I say about the upper limits on the ellipticity, right? So the ellipticity, again, being the size of the mountain. What can I say about how big the mountains are on this pulsar? And this is what you're seeing here. What you're seeing is on the vertical axis is the ellipticity, on the horizontal axis is the gravitational wave frequency. So what they did was they took all of these stars over here, as well as these the triangles for the spin down limits. They took all of these data points, they plugged it into this equation, worked it backwards for their distances, and they said, what can I say about the size of mountains on these objects? And so up here, at the lower frequencies, these are the young neutron stars. And with the young neutron stars, you can see that even though we can probe them, even though our search results can be pretty sensitive for the young neutron stars, we can't say that much about their ellipticities. We can only say, for instance, on the crab, the size of the maximum mountain is less than about a meter or so. For these really old neutron stars over here, some of these pulsars, some of the ellipticities go all the way down to 10 to the negative 8. So we can say in that case, the size of the largest mountain on that neutron star is less than 0.1 millimeters. So this is what we do in our CW. We find our upper limits. We find the upper limits on our strain, and then we work it backwards to say, what can we say astrophysically about this source, about this set of sources? So if we don't know the actual ephemeris, but we know the age, or we have a guess on the age, maybe, right? So there's some supernova remnants where if you look back into history, you can see a recording where someone said there was a supernova in 1663 or 68, there was a supernova in 1004. So you can say if it's expanded this much, then we can work backwards, use our particle acceleration codes to work backwards and say this supernova remnant, we expect the supernova to have occurred about 10,000 years ago. So you do things like this where you can kind of get an estimate on the age. If you know the age, then you can know the age-based limit. So this goes back to the breaking index, right? So I said yesterday that the frequency, as frequency to some sort of power. The spin down goes as frequency to some sort of power. What that power is depends on how that star is losing energy, right? If it's losing energy due to pure dipole radiation, so magnetic dipole radiation in this case, for the most part, breaking index is going to be 3, so it's going to be evolving in one way. If the radiation mechanism, so gravitational wave emission, then the breaking index n is going to be 5. And so what you do is you say, I don't know exactly how it's losing energy, but I'm going to take the maximum possible. I'm going to take the most conservative amount, and I'm going to say it's losing energy as fast as it can, basically, all gravitational quadruple energy. And then I work backwards and say, based on this, the fact that it was born, and then it was only emitting due to gravitational quadruple emission, then what is the max amount of energy it could have lost during that time? So when we do this, we see that the best sources for these type of directed searches are young neutron stars. So one of our favorite sources is Cas A or Cassiopeia A. This is a supernova remnant where when you look in the X-rays, you can see a hot source, a high temperature source that seems that, so neutron star has not been detected, but the high temperature source basically is more easily fit with assuming there's a neutron star than a black hole. Depending on who you ask, it could still be a black hole. But let's say, for the sake of argument, it's a it's only about a couple hundred years old. Only about a couple hundred years old. It's at 3 kiloparsecs from us, so it's a little bit farther than we'd like. We'd like things that are, I think the closest ones are hundreds of parsecs. Those are also older. Based on this, say you calculate a spin down limit, or an age-based limit of 10 to the negative 24. And I said before, I'll show you the results. So this is the age-based limit, and we went through. Can we do better than that? So what you're seeing here, again, is the strain, 90% strain, or upper limit on the strain versus search frequency. In the red are the results from this search that I'm showing you, which is one of the more recent ones, although this is still on actually initial LIGO data, and we're working on the results for advanced LIGO data right now. So what you're seeing here is the strain on, the upper limits on the strain, and let's see, what do I want to say with this? Yeah, so the age-based limit is around 10 to the negative 24, is that horizontal dashed line. And basically, for the entire search frequency that we're looking at, we are actually below that. So we are in a regime where we can start to say something interesting, right? Because if we were above that, then there's no point in doing this search, basically. We would never, there's no physical reason why we would have detected anything. And now we're at least saying we might have detected something, or we might detect something in the end. So you play the same sort of game where you say, you work backwards and you say, if I know the upper limits on strain, I can figure out the upper limits on the size of the mountains. This is a little bit targeted pulsars, or sorry, with the known pulsars. It was, as you said, I know this pulsar is emitting, or I know this pulsar is spinning right there, and therefore I know this pulsar, the ellipticity must be less than this. The problem is, with something in a directed search, with something like Cas A, you don't know exactly what frequency it's spinning at. So then you have to say things like, assuming it's spinning at a frequency of 400 hertz, or sorry, assuming it's emitting gravitational waves at 400 hertz, which means it's spinning at 200 hertz. Assuming it's emitting gravitational waves at 400 hertz, then I know the maximum mountain on that neutron star has to be less than, was it 10 centimeters or 100 centimeters? What am I going? 10 to the 4, 100 centimeters, right? So the large mountain must be smaller than 100 centimeters. But if instead it's emitting at 800 hertz, then the largest mountain must be larger, or it must be smaller than some tens of centimeters. And so with this, you kind of have two steps. One, you say, assuming it's emitting at this frequency, what does that tell me about the maximum ellipticity? So, right, for a directed search, neutron stars, isolated neutron stars that we know in supernova remnants, for instance, are great. But we can also look at neutron stars in accreting binaries. So this is going back to Scorpius X-1 that I talked about, the low-mass X-ray binary, where there's a neutron star, and then there's a companion, and the companion is overfilling its Roche lobe and giving some material to the neutron star. That material falls onto the magnetic poles, heats up the magnetic poles, might also deposit material there, might also cause a mountain to form there. So what I'm showing down here, right? So what I'm showing down here is the set of, let's see, this is the spin frequency. This is a distribution of spin frequency for low-mass X-ray binaries, and in particular for low-mass X-ray binaries that have neutron stars. So these are other neutron stars in low-mass X-ray binaries, usually pulsars, I think, that you can measure, so you can measure how fast it's spinning. The breaking so as the neutron star is accreting material, it's spun up, and the break speed, so the fastest possible it could be spinning before it breaks up, is around 1,000 hertz. So there's nothing stopping it from going all the way up to 1,000 hertz. And there is one that does, right? There is one that seems to be spinning at around kilohertz. But there also seems to be the pile up at 600 hertz, right? There's not much, and this is also a small number, right? Small number statistics. But if you look at it, there seem to be a lot of neutron stars that are accreting material that should be able to be spun up to 1,000 hertz, and yet they're all kind of piling up and stopping at around 600 hertz. They don't seem to be spinning up any more than that. And so then you have to say, if this is true, if there is some sort of pile up at 600, 700 hertz, then it's being spun up by accretion. It must also be slowing down for some other reason. There must be some other braking mechanism for it. Maybe maybe there's something going on with the it's emitting magnetically. So maybe it's losing emission electromagnetically, but maybe it's sorry, coffee not quite kicked in yet. Maybe instead it's losing emission due to gravitational wave radiation, right? Because, like I said, that material is falling onto the poles. If material is falling on, then you could say maybe there's a mountain being formed, and if the mountain's being formed, it's going to be emitting gravitational waves, and so maybe that's what causes this pileup. And this is what we call torque balance. This is what we call the torque balance, the whole torque balance limit, right? So before I said if you know exactly how fast it's spinning down, there's the age-based limit. So for neutron stars and accreting binaries, there's the torque balance limit. Speaking, how does this work? So we say, all right, the neutron star is emitting gravitational waves. It's also accreting, and we say that it's because the frequency has stopped stalled at around 600 hertz. Then whatever energy it's gaining over here, it must be losing over here. So there's the balance there. And we also say if it's accreting over here, if it's accreting a lot of material at once, and we actually see this, we see flares from these low mass X-ray binaries, and that happens when a lot of material gets accreted at once and then gets emitted, right? So you get a flash, I think usually X-rays. And so what you do is why do I have all these? What you do is you look at the amount of energy that's being emitted in these flares, you equate that to the amount of energy that must be deposited, or the amount of matter that must be deposited based on how bright the flare is, and then you say, based on that, then I can say all of that energy is being emitted in gravitational waves. Assuming all that energy is being emitted in gravitational waves, what are the strains? Yep. Sorry, what will? What will cancel the recoil? You mean by the recoil? Sorry, I'm not quite understanding the. Yeah. Yeah. Okay. So in this, but So the question is, when you emit gravitational waves, if there's the reactive recoiling, right, from that. But in this case, right, keep in mind that the gravitational waves are being emitted uniformly. Right. So it's just like in the CBC case, in the binary coalescence case, right? When they're rotating around, the gravitational waves are being emitted all around, right? All isotropically. And so it's similar for this case, where you just have a bumpy neutron star and it's just spinning around. Again, the gravitational waves are just coming out like this. And so there's no net momentum that's being imparted to it. So our favorite target for these searches for accreting neutron stars is Scorpius X-1. This is also around 3 kiloparsecs away. We haven't detected any pulsations from it, but this is the one with the brightest X-ray flares. And so, like I said, we say the energy emitted in X-ray, or the energy that we observe in the X-ray flares, with higher energy there, with brighter X-ray flares, means more mass was deposited, or that we make that assumption that more material was deposited. More material was deposited, more energy was converted, and so more energy is available to be emitted in gravitational waves. So this is why we search for Scorpius X-1. This I'm showing a plot, an upper limit plot. So in CWs, all you have are upper limits, basically. So far. We'll see one day. So what I'm showing again is a plot, the upper limit on strain versus the frequency of the source. This dashed line down here is the torque balance limit. And so unfortunately, so like I was saying before, we always do things like say, can we do better than this limit? Can we do better than this physical limit that we know the amount of emission is less than this amount? And unfortunately, for Scorpius X-1, which is our accreting neutron star to search, we're actually not quite there yet. We're not quite there yet partly because searching for objects that are in binaries is a lot more expensive, right? Not only do you have to take into account the Doppler modulation of the Earth, you also have to take into account the Doppler modulation of that object as it's going around in the binary, right? As it's going around the binary, there's also that inherent Doppler modulation from that to the frequency. And sometimes and with all of these, with Scorpius X-1, we roughly know what the orbit looks like, but we don't know to incredible accuracy, not to the accuracy of pulsars and things like that. So that's why the search is more expensive. It's a lot more expensive and it's a lot harder. It's really hard to run a search for binaries that's all sky, right? Because again, for standard all sky search for isolated sources, you just have to demodulate for every point in the sky. And for a search for an all sky search for binaries, it's not only demodulating for every point in the sky, but also every type of binary orbital parameter, every type of orbit that you are interested in looking for. And so what I'm just showing here, what you have here in the black and the purple and the green, these are just the results from different type of searches. And these are all done in advanced LIGO data. And so you can see they have slightly different sensitivities, but they also make different assumptions. So cross-core, the one down here, is the most sensitive, but pretty sure. So it's the most sensitive. It's also the one that makes the most assumptions about what the signal looks like. The other two, radiometer. This is one that kind of more or less looks for sort of power, right? So it doesn't really require any particular signal model. And this one, Viterbi, which is in the middle here, it's kind of also in the middle of these two things where it looks for power accesses, but it looks for tracks. So it looks for tracks that look kind of like CW signals that you would expect the signal to be, but it doesn't say the signal has to be like this. Sky searches. So all sky searches are a bit more complex, right? So what I'm showing here is the results for the a recent low frequency search. And I guess the main thing I want to say here is going back and sensitivities, right? For the known pulsar search, the sensitivity, the upper limits go almost down to 10 to the negative 26, right? So these are going all the way down to almost 10 to the negative 26 in the most sensitive parts of the detector. 10 to the negative 26. For a directed search, isolated, we go down to a few times 10 to the negative 25. For a binary search, again, a few times 10 to the negative 25. For an all-sky search, oh yeah, okay, negative 25. So the difference, right? So the difference is also that these searches are done in slightly different data sets and different things as well. But yeah, overall, I mean, the thing is that basically the more let's see. Yeah, the more you know about, so the known pulsar search, right? You know the most about them. You can go the most sensitive, get the most sensitive search out of it. And then when you don't know as much, you can't do as well. But you can maybe say more about different types of sources. And this is a little bit tricky, but right, I'm saying that you could take your upper limit on strain and convert it to an upper limit on ellipticity. You can do the same for an all-sky search, but then you have to make two assumptions. And one assumption is saying, first, you have to set your distance, right? So you say, I'm assuming a source at 1 kiloparsecs. So that's the pink one. And I'm assuming it's emitting at 60 hertz. Then the mountains have to be smaller than 1 meter. On the other hand, if something is 10 kiloparsecs away, so roughly at the center of the galaxy, then the mountains, I don't know, have to be smaller than 10 meters, right? So this is the game you play with distances, ellipticities, strain, things like that. Just showing another set of upper limits for an all-sky search. This was a wider frequency band. This goes all the way to 2,000 hertz for these are again different pipelines, right? Again, because each pipeline does things a little bit differently, makes different assumptions. Some are more sensitive, but those sensitive ones are also oftentimes more plagued by detector disturbances. Because if they're really good at picking out signals, they're also really good at picking out disturbances. So in the last little bit of time, I have to go over the post-processing, right? So we get our searches, we send our searches out to Einstein at home, the whole network comes back months later, and then we're left with the problem of what do we do with 10 to the 17 search results? So this becomes a question of big data. And so with big data, a lot of times, we've automated a bunch of procedures, and we started off by doing things like saying, find the loudest signals, right? Because we can rank all the signals. So we pick the loudest ones and we say, if we think that the underlying distribution looks like this, then what's the significance of the loudest signal? But then there's a lot of tricky things that there are a lot of other things you could do, like we're starting to look into sort of machine learning algorithms and things like that to try to, because sometimes these algorithms can do better, this machine learning processes can do better than humans can, and so we're working on all of these different techniques to try to pick out signals and try to analyze our data faster. In theory, your noise is really well behaved. In theory, your noise is well behaved. It's very flat. If your noise is really well behaved, the distribution you expect, it's fairly well understood. It's analytical and it's very well behaved as well. And in that case, if you have a potential signal, it's easy to quantify its significance. Because if you know the expected distribution looks like this, then you can say, all right, if this is the standard deviation and this is the sigma, then our signal is at 6 sigma, let's say. And it's relatively straightforward to calculate. But that's only if your noise is well behaved, right? This is what you require. And in reality, the data looks more like this or worse. Because with this, at least there's sort of a visible disturbance on here, right? There are a lot of disturbances that are not actually visible. There are a lot of sort of these excesses that are below the level of the noise, and they only come out when we run the most sensitive searches on them. But so here's the problem, right? If your entire distribution looks like this, and you have a potential signal that's all the way out here, how can you even start to quantify what that significance is when you can't know whether that's actually a disturbance or whether that's true signal and what the significance is? So what you have to do first step with these 10 to 17 trials, you have to go through and you throw away anything that looks like that, and you only keep things that look like this. We do this in a semi-automated way. What we do is we divide our data into 50 millihertz bands. So we have, let's say, 100 hertz or 1,000 hertz search range. We divide it into 50 millihertz at a time. And we say, let's look at this 50 millihertz band, the results from this, and so this is what on the vertical axis is spin down, horizontal is frequency. Let's look at this 50 millihertz band, the whole search parameter space for the 50 millihertz band. Let's divide it up into, let's say, 10 by 10 squares, and let's calculate the density of points in all of these squares. And on the left, what you see is if it's completely undisturbed, then the density is very flat, it's very uniform all throughout. If there is a detector disturbance, some squares are going to be particularly hot or particularly dense, and other ones are going to be particularly sparse. And so what you do then is you say, comparing, you take the densities or the max densities for all of these 50 millihertz bands, you compare them, and you say, there's this large range of densities here where everything looks kind of flat, and then there are all these ones over here where there's some sort of excess that's not consistent with being flat. And so that's the sort of thing we do to try to get rid of, in a semi-automatic, get rid of things that look like this. And that's the first step. And if you're successful, right, if we're successful, then we're only left with clean bands. So what we see here on the left is the detection statistic. So this is the maximum and minimum detection statistic for all these bands. And you can see there's a lot of lines in here, right? You see there's a lot of lines in these detectors or in these search bands where things are not consistent with being uniform. So what we do is then we make a cut and we say anything above a 2F of this or below a 2F of this, we're going to cut from our search. When we do that, we have something that's very clean, and we can then put these results through, only these search bands through our automated algorithms. Then what you do is you say, all right, you can calculate the loudest expected value. If you only have noise, if you only have flat, stationary Gaussian noise, you can calculate analytically what you expect the loudest expected value, statistic value for that number of trials in Gaussian noise, in stationary Gaussian noise. If you have n trials, you just multiply that and you get a distribution for the loudest you expect in n trials. And then if you know that, then you can take your loudest and you calculate the significance based on the loudest expected. So this, at this point, becomes kind of a math. I guess, yeah, and then when you do that, right, then you convert that into significance. I'm going to go over this kind of quickly. And then when you have a significance, you have sigmas, you convert p-values. You convert those into p-values and you say, is there anything that deviates from what I expect? And here in the blue is what we observed, and the black is what we expected. There's some small deviations because these methods are not quite perfect. Things are not quite Gaussian and perfect. But for the most part, there's no glaring signal out here. And usually this is what happens. Sometimes this is what happens. So these are two different searches. What I'm showing is the one on the right is an all-sky search. In advanced LIGO data, the one on the left is a directed search and initial LIGO data. Right? Initial LIGO was running for a while, so by this point we kind of knew the detector really well. Advanced LIGO, a lot of new upgrades, but also a lot of new detector disturbances. The green line is the expected, and the blue dots are the blue data points are all the things that we actually measured. So what is this saying? Is this saying that we have all of these really high significant, because this p-value goes all the way to 10 to the negative 13. Am I saying we have all of these really high significant signals? Well, no, because be detector disturbances. And how do we know if it's a signal or detector disturbance in the first place? We can do, one of the things we can do is run a follow-up search. So in a follow-up search, here's the idea. So we talked about starting out with the difference between coherent, semi-coherent searches, right? In a coherent search, things are more expensive, but a lot more expensive, but more sensitive. What we do is we have our initial search, so that's stage 0 up there. And in that initial search that has however many segments that we have, then we take the interesting candidates, the loudest candidates from that initial stage, and we graduate them forward to stage 1. And in stage 1, we increase the coherence time, right? And when we increase the coherence time, we increase the sensitivity. We also increase the computational cost, but now instead of searching our entire parameter space, we're only drawing little targets around, let's say, 10,000 candidates. And then we keep doing that until we get to a final fully coherent stage. And in this scenario, what you expect is that when you go from the initial stage, the initial search, to later and later stages, you expect Gaussian fluctuations. If it's just a fluctuation, when you search for it deeper and deeper, you don't expect it to increase in significance, right? It's just going to level out. But then you expect the signal to increase in significance. Now here's the problem. Detector disturbances can also increase in significance just like signals, because like I said, right, one detector disturbance that we found was a blinking LED. Well, if you search for, it's always going to have that one frequency, right? It's going to look like a signal no matter how deep you search around it. So let's see. Oh yeah, I already talked about these. Yeah, and so you can see again, so this is the amplitude spectral density of the detectors. You can see all these lines. We talked a little bit about these lines, but for every line you see in this plot, there are many, many you can't see. That are underlying, that are below this level that you can see with the human eye. So just last thing I want to talk about, this is to give you an idea of what sort of things I do. I work on data analysis right now. I used to work on astrophysics and astrophysical analysis, observations. Now I work on data analysis. What does that mean? That means developing methods and tools for dealing with things that pop up, for searches, for running new searches, for finding new targets to run searches on, as well as for dealing with things like all of a sudden we have tons of detector disturbances that we don't know what to do with. And so this is the type of video that we came up with recently. So if you remember, we said that a signal coming from space, astrophysical, coming from over there, the Earth is rotating and orbiting. So an astrophysical signal is going to be Doppler modulated as the Earth does its thing. Detector disturbances come from the Earth itself, right? They come from the detector. The detector disturbance is not going to be Doppler modulated throughout the search. And so that's really all it is. The fact that don't worry about the specific words, but the astrophysical signals are going to exhibit this modulation. The detector disturbances, which are from the Earth, are not. They're going to be relatively flat, right? And so what you do is you run these two types of searches. Basically, you can run a search. If you just turn the Doppler modulation off, you can run a search where all of a sudden you're more sensitive to things on the Earth. And so when you do that, you can compare and say, if I have something here and I run a search that's expecting an astrophysical signal, then I run a search that's expecting a terrestrial signal, is it more significant in this search or in this search? And when you do that, so this is an example of when we did that to something from a previous search. This is exciting to me. This was very exciting to me. I don't know if this is going to be exciting to you guys. But what you're seeing here on the left, this is a fake signal. So this is a fake signal that we put into the data. And the blue is, the orange. The orange is what happens when you search for it using an astrophysical signal waveform. So if you have an astrophysical signal and you search for it with an astrophysical signal waveform, it's going to be very loud. If you search for it with the terrestrial waveform, it ends up being completely quiet. And this was something that we we didn't expect it to be so significant, this huge jump, where the astrophysical signal disappears entirely into the noise. What you're seeing on the right here is this orange in the back was the results from the original search where we had something that was relatively significant, and we didn't know if it was a signal or a detector disturbance. And it turns out with the blue, when we ran the new search over it that looked for terrestrial signals, it actually got more significant and it really popped up above the noise. So we do things like this and we say, does it look more like an astrophysical signal or a terrestrial signal? Which one gives you a higher significance? And yeah, and then the goal is to discard anything that doesn't behave like a signal. I guess don't worry about exactly the details of this plot here, but the goal is to discard anything that doesn't resemble a signal, right? Because we have a signal waveform. We don't have a waveform for detector disturbances because they could be anything. And so what we do is anything that doesn't look like a signal, we can throw away. We can safely throw away, at least a standard signal. And so when we do that, this is the last slide, and the result was that you do this, you can do things like discarding almost all of your candidates, right? And so you discard when instead of having tens of thousands of candidates that you don't know, or signal candidates that you don't know what to do with, you run this search on them and you can actually discard almost all of them. What we were left with were 4 signal candidates that had survived everything, including this last stage. And so then the question becomes, what do you do with it? So what do you do when you still have candidates you can't kill, right? So what we're talking about is just killing these signals, right? Or killing these signal candidates because we don't think they're actually signals, or at least putting them through a lot of tests to make sure they really are or are not. You do. The first thing you can do is wait for new detector data. Because if you have a search in this time span and you expect the signal to look like this, you wait a little while, the detector turns on again, that signal should still be going on. So you can search again in this detector data. You can, in fact, since maybe you found it over here, you can actually go back in time and say, maybe even though the data was less sensitive here, at least I know exactly where to look now, and then you can search for it over here as well. So you can search for it in different spans of detector data. Another thing you can do is try to look for non-standard CW signals, right? So far I've been talking about signals that persist, that are only defined by frequency and a spin down. But we talked about glitching neutron stars. Neutron stars, especially young neutron stars, are glitch fairly often. So what you can also do is you add 1 more or 2 more parameters, or a couple more parameters to your search, and you say, instead of spinning down just normally, just kind of well-behaved way, what if it spins down and then it glitches and then it spins down again? And when that happens, after a glitch, you expect the frequency to have changed, you expect the spin down to have changed, and you expect the strain to have changed, right? So you expect, and you also maybe and also you don't expect coherence in between before and after the glitch. So you can do things like that where you search for slightly non-standard signals, but at the end of the day, sometimes all you can do is say, this just doesn't look like a standard CW signal, and maybe just, I don't know, maybe in the future, it's kind of unsatisfying, right? Because maybe in the future we'll be able to say something like, if you have a signal over here, a signal candidate over here, and you look in new data and you don't see anything, maybe there isn't anything there, right? Maybe what you saw over here was just detector noise, or maybe something has changed to the situation, to the neutron star in here. So the most you can say is that you don't find anything consistent with this signal in this data. So these are the games you play when you are a CW data scientist, and these are this is just sort of an overview of the methods that one type of CW search does. Are there any questions? I know everyone's really tired. Yeah, so the question is what's going to happen when LISA is functioning? Will we have more sources, or what kind of sources? So because LISA is in a different frequency band, they're going to be different sources. So LISA's sources are going to be merging supermassive black holes. As far as sort of coming from a continuous wave standpoint, some of the LISA sources will be sort of more CW-like, but the thing I was talking about yesterday with the supermassive black hole binaries, that's almost more, that's really CW-like, right? That's a steady state source, basically. So with LISA, there's some overlap in terms of things like, so from a data analysis standpoint, there's some overlap in terms of analysis methods, because with each new generation, you want to learn from the old generation. You also want to bring in new methods and things like that. So there's a little bit of overlap, and there's also overlap in the people, but a lot of times the actual physical sources are going to be different. That's a good point. Yeah, I forgot about that. Yeah, so one of the LISA sources, right, is Weisdorf binaries, and that's actually, but that's actually expected to be a stochastic background, I think. Yeah, so that's the problem, right? So with continuous wave sources, so there's some similarities between CW sources and stochastic background sources, right? The stochastic background just says you have so many of these sources and these regular sources that they all add up to just some indistinguishable background. So the white dwarf binaries which Lisa will be able to detect signals from or could detect signals from, there's so many of them in the would expect to just be a background. But I guess I don't know exactly. So with that's true, right. So yeah, so that's the thing. So there's going to be in all of these, right, there's a background I say, but there's always going to be a couple that could stand out from the group from the crowd. And yeah, so there are always going to be a couple that are going to be sort of more CW like. And on a similar note, when I was saying with the pulsar timing array and how they're looking for supermassive black hole binaries and how that's sort of a stochastic background, also get a couple of especially loud signals from that, and you could actually, if the pulsar timing arrays get sort of sensitive enough, you could actually get CW type signals from that as well. So there's a lot of overlap between CW and stochastic, which is also why remember so some of the searches, actually some of the things we look for, stochastic searches look for the same things. They just look for them in slightly different ways. They look for power excesses. We do more modeled searches. Any other questions? If not, let's go get some coffee.